Welcome to section 3.2, describing bivariate quantitative data. In this section, we go beyond looking at single variables. We're now interested in how two quantitative variables might relate to each other. For example, does more studying lead to higher test scores? Do students who get more sleep tend to exercise more? These are all real questions we can begin to answer using scatter plots, correlation, and regression lines. Bivariate quantitative data means we're analyzing two variables that are both numeric. For example, we might look at hours worked per week and the amount of money earned, or hours spent gaming and GPA. These pairs of data help us understand how two continuous variables move together. We want to explore the direction of that relationship, its strength, and whether it can be modeled in a useful way. To visualize these relationships, we use a scatter plot. Each dot on a scatter plot represents a single observation. In other words, one pair of values, x, y. For example, if one student studies 8 hours and scores a 75 on the exam, we'd plot a point at, oops, not working, there we go, 8, 75, right? That's a point on the graph. The x-axis usually represents the explanatory variable, the one we think might be influencing the other. And the y-axis shows the response variable, the outcome we're interested in. Looking at the pattern of dots can tell us whether the relationship is linear or nonlinear, positive or negative, and strong or weak. To decide whether a scatter plot shows a linear or nonlinear relationship, look at the shape of the pattern formed by the points. If the dots generally follow a straight path, even if they're not perfectly aligned, that's a linear trend. For example, if we plotted a person's weekly study time and their exam scores, we might expect a roughly straight line relationship. More hours, higher scores. A nonlinear relationship curves. It might rise quickly and then level off. That would be nonlinear. Or it might form like a U shape or some other pattern that's not aligned. For example, caffeine intake versus hours of sleep might show a curve. A little caffeine boosts alertness, but too much could interfere with sleep, reversing the trend. The direction tells you whether the relationship is positive or negative. In a positive relationship, both variables increase together, like hours studied and test scores. As the x increases, goes this direction. The y's go up. That results in this, a positive pattern. In a negative relationship, as one goes up, the other goes down. So we have this pattern. Think of hours spent binge watching and GPA. More TV might mean less time for schoolwork, leading to lower grades. The strength of the relationship depends on how tightly the points cluster. If they hug a narrow path, the relationship is strong. You can confidently say one variable helps predict the other. If the points are widely scattered, the relationship is weaker. A strong trend tells us there is consistency in how the two variables behave together, while a weak trend says the relationship is noisy or inconsistent. Think of strength this way. Imagine plotting height and shoe size. You'd expect a fairly strong relationship. Taller people usually wear larger shoes. But plot hours spent on social media and amount of water consumed. Even if there's a pattern at all, it might be weak and less reliable. Let's look at an example involving 10 students. Each student reports how many hours they studied in a week and what score they received on a major exam. When we plot these as a scatter plot with hours on the x-axis and score on the y-axis, we start to see a pattern. Now, this would form one point. This is the point 465. So in my XY plane, I would locate 4 and 65 and draw a point there to represent this first data point. Keep doing that for all of these data points. But this is a perfect opportunity to create the chart together in Excel. Once plotted, we'll see whether more study time is linked to higher scores. Now, I already have this data here in Excel. So we're just going to highlight both of them. Go over here to Insert. And there's our scatter plot. Just as before, we want axis titles. So this is hours spent studying. This would be my exam score. And we give the chart a nice descriptive title. Just as before, we can change the colors, we can change the axes, we can do lots of different manipulation. Once we have our scatter plot, first thing to do is look at the form. Is the relationship linear or curved? In this case, the data follows a straight line trend, which means it's linear. Next, we check the direction. Here, as X increases, more hours, Y also increases, higher scores. So we call this a positive relationship. And finally, we assess the strength, how closely the points follow the line. If they cluster tightly around a straight path, the relationship is strong. If the points are more scattered, the relationship is weak. Here we see they're pretty clustered around a line, so this looks like a very strong relationship. What is correlation? To describe the direction and strength numerically, we use correlation denoted by the letter R. Correlation ranges from -1 to +1. A value near +1 means a strong positive relationship. As one variable increases, the other tends to increase too. A value near -1 means a strong negative relationship. A value close to 0 means no linear relationship. The formula for correlation is the covariance divided by the standard deviation of X times the standard deviation of Y. We're going to learn about that covariance in just a second. But what this does is it standardizes the covariance by dividing by the product of the standard deviations. That way, R is always between -1 and +1 and does not depend on the units of the variables. To get the correlation, we first need to compute the covariance, a measure of how X and Y move together. If high values of X tend to pair with high values of Y, the covariance is positive. If high values of X go with the low values of Y, the covariance is negative. The formula for sample covariance is the deviations of the X, the data point minus the mean, the deviations of the X, times the deviations of the Y, the data point minus the mean. Multiply those together, add them all up, and then divide by 1 less than the number of points we have. This formula looks a lot like the one for variance, but here we're multiplying by the deviations of X and Y together. It gives us a sense of whether the variables tend to increase or decrease together. However, the units of covariance are messy. For example, it would be hours times points, which is why we standardize it into R. All right, so let's look at how to calculate the covariance of the data that we are working with here. Okay, so I want the covariance of the X and the Y that's there. So we're going to go covariance dot S because it's a sample, not a population. And we're going to put in our array. So our X scores are A2 through A11, and the Y are B2 through B11. You know what? I want to move this here because I want to label it. This is S sub XY, our covariance. Okay, now the positive sign tells us that as hours studied increases, exam scores tend to increase as well. The magnitude isn't standardized, so we won't compare it across data sets, but it's useful for computing the correlation R. So now let's look at getting that correlation. So our formula for the correlation is that covariance, and we also need the standard deviation of X and the standard deviation of Y. All right, so to get our standard deviation of the X's, and the standard deviation of the Y, so our R, the correlation coefficient, that formula was the covariance, which is B13, divided by the product of the standard deviations. So that's a B14 times B15. So we get a correlation coefficient of 0.99 about. That's very close to 1, suggesting that the points follow a tight linear pattern. This confirms what we saw in the scatter plot. Students who study more tend to score higher. Since R is unitless, it allows us to compare strength across data sets, unlike covariance. Once we've confirmed there's a linear relationship, we often want to model it to describe the trend with a line. That's where the least squares regression line comes in. It's a line that minimizes the total squared distance between the observed Y values and the predicted values on the line. The equation looks like this. Y hat, the predicted Y, is equal to A plus BX. And if you remember your algebra, you remember A is the y-intercept and B is the slope. So that slope, B, tells us how much Y is expected to change when X increases by 1 unit. A, the y-intercept, is the predicted value of Y when X is 0. So to calculate the slope B of the regression line, we use the formula that B is equal to the correlation coefficient times the standard deviation of Y divided by the standard deviation of X. This tells us that the slope depends on both the strength of the relationship R and the ratio of the variable standard deviations. To find the intercept A, we plug into A is equal to Y bar, the mean of the Y's, minus B, the slope, times X bar, the mean of the X's. That gives us the line starting point based on the mean of X and Y. This way, the line always passes through the point X bar comma Y bar, which is the mean of the X's comma the mean of the Y's, right? Okay, let's look at how to calculate these on Excel. So, we already got our standard deviation of X and our standard deviation of Y and the R, so we can jump right into calculating the B. According to the formula, it is R, which is B16 times SY, the standard deviation of the Y, that's B15 divided by the standard deviation of the x, that's B14. So there's our slope, 1.98. Now, to get A, we're going to need the means. So I want to do the average of the x and the average of the y. All right, so average A2 through A11 and average B2 through B11. All right, now we can get A according to our formula, right? It is the average of the y, which is B19, minus our slope B, which is B17, times the average of the x, which is B18. All right, that means our equation looks like y is equal to A, which is 58.7, plus B, which is 1.98, times x. So, for example, if somebody studies for 12 hours, we would expect their score to be 58.7 plus 1.98 times 12, or about 82.46, something like that. Okay. Now, we showed how to do it, calculating out all those formulas. There is another way to do it. We can go up here to data, data analysis, find the regression, plug in our y input range, plug in the x input range, plug in the output range, and we see our R, R.988, that matches the R we found. The y-intercept, 58.67, that matches the y-intercept we found. 1.97, that matches the slope we found. So we can also read it directly off of there. Okay, so to sum up, we saw how to get the equation in Excel. We could have used the formulas as well. To predict the score for a student who studies 12 hours, we just plug into that regression equation. 58.67 plus 1.98 times 12, we get 82.43. That's a powerful use of this model. We can now make informed predictions. Let's interpret our regression equation. The slope, 1.98, tells us that for every additional hour studied, we expect the student's exam score to increase by about 1.98 points, assuming the trend holds. The intercept, 58.67, tells us the predicted score for someone who studied 0 hours. This isn't always meaningful. We wouldn't expect someone to score 58.67 without studying, but it's part of the model. Always interpret slope carefully. It tells us the effect per unit change in the explanatory variable. So to summarize, scatter plots help us see relationships between two quantitative variables. Covariance describes how the variables change together, but its units are hard to interpret. Correlation, R, standardizes that measure, and tells us direction and strength. If the relationship is linear, we can model it with a regression line to make predictions. The slope and y-intercept come from R and the means and standard deviations. These tools are foundational for deeper data analysis, and they're incredibly useful in real life, predicting success, comparing behaviors, forecasting trends, and more. And remember, correlation does not imply causation, as our happy little AI capybara friends will tell you.